In this section, we discuss the electrical conductivity of doped semiconductors and the three types of behavior that can be exhibited. In section 5.1, we discussed intrinsic semiconductors, where electron and hole pairs are thermally excited. A doped semiconductor can also behave as an intrinsic semiconductor when the dopant concentration is less than the thermally excited electrons and holes. In this case, because the thermally excited electrons outnumber the dopant electrons, we can approximate the number of electrons from the intrinsic concentration. The intrinsic concentration is large at high temperatures and small band gaps. Normally, when we dope a semiconductor, we try to make it an extrinsic semiconductor by using a concentration of dopants greater than the intrinsic concentration at the temperature we plan to use it. This allows us to precisely control the number of free carriers. If we were to reduce the temperature such that kT is less than the defect energy, we would enter the ionization regime. In this regime, we say that many of the defects are not ionized, trapping their carriers such that the carriers are not in the mobile conduction or valence bands. In this case, then, the number of free carriers is less than the dopant concentration. The fraction of these ionized impurities can be estimated using an Arrhenius equation where the ionization energy is the energy in the exponential. If the defect energy is large enough, we can see all three regimes in the same material as a function of temperature. If we plot the logarithm of the charge carrier concentration versus 1 over T, we should get three straight lines that merge into one another due to the exponential dependence of N versus energy. At high temperature, when 1 over T is small, we expect the material to be in the intrinsic regime, where the number of free carriers is determined by the band gap. As we reduce temperature, we reach the extrinsic regime, where the number of free carriers is the number of dopant atoms. At very low temperatures, or for deep defects, we may reach the ionization regime, where the number of free carriers depends on the ionization energy. The conductivity in the intrinsic regime is sometimes used to estimate the band gap of the semiconductor. This is because the slope of the logarithm of the charge carrier concentration versus 1 over T should be simply the band gap over 2 kT. We see here that germanium with a smaller band gap has a lower slope than gallium arsenide with a large band gap. The experimental log conductivity versus 1 over T will show a similar behavior with slope proportional to the band gap. This assumes that the effective density of states times the mobilities are not very temperature dependent, which turns out to be a good approximation at high temperature. Recall that we derived for a metal the electron mobility due to scattering of electrons by atom motion is proportional to 1 over T. We got that by assuming the scattering cross-section is equal to the area within which the atom vibrates, which is proportional to kT. Then, because in a metal the average speed of the electron is the Fermi velocity, we got tau, and therefore mobility is proportional to 1 over T. For a semiconductor, we do a similar analysis, except that for the average speed of the electron, we use the thermal velocity of the electron. This is because our semiconductor obeys Boltzmann statistics as opposed to the Fermi statistics for the metal. For the semiconductor, the thermal velocity comes from the kinetic energy equal to kT, bringing in a square root of T into our thermal velocity, which goes into the tau, and therefore the mobility, giving us an overall mobility proportional to 1 over T to the 3/2 power. In our doped semiconductors, we also have a scattering by ionized impurity due to the defect dopants. So in this case, the tau will also depend on the number of impurity atoms. Because fast electrons are less scattered by the Coulombic attraction to the impurity than slow electrons, the scattering will depend on the energy of the electron. It turns out that we can approximate the effective radius for the scattering cross-section for when the kinetic energy equals the potential energy. The potential energy for a Coulombic attractor is proportional to 1 over r, whereas the kinetic energy is proportional to kT. In this way, we have 1 over r is proportional to kT. Because tau is inversely proportional to the cross-sectional area, the velocity, and impurity concentration, we end up with tau is inversely proportional to r squared from the area, the thermal velocity, and then the impurity concentration. Substituting kT for 1 over r gives us a kT squared on top divided by a square root of kT from the thermal velocity, overall giving us a mobility proportional to t to the 3/2 divided by the impurity concentration. The scattering of electrons by ionized impurities is a major contributor to the decrease in drift mobility with increasing dopant concentration, as we have derived here. We can use Mathiassen's rule to combine these two effects into an overall or effective mobility for electrons or holes in a semiconductor. At room temperature and above, we tend to see drift mobilities decreasing with temperature due to lattice scattering. However, at low temperatures and high defect concentrations, we sometimes see mobilities increasing with temperature due to the contribution of ionized impurity scattering. This temperature dependence of the mobility, then, will give us a different dependence on the logarithm of conductivity that we saw from the logarithm of the carrier concentration. Most notably, the lattice scattering gives us a decrease in the conductivity for higher temperatures in the extrinsic regime. If we are measuring resistivity as a function of temperature, we will see in our extrinsic regime a slight increase in resistivity for our semiconductor, like we see in a metal. Although we sometimes distinguish semiconducting behavior from metallic behavior looking at the temperature dependence of the resistivity, we see that by using dopants, we can achieve metallic-like behavior in an extrinsic semiconductor.